Hey everyone. Today we're going to be learning about concentration, specifically two new types of concentration, such as molarity and parts per million. We've already covered a few different types in previous lessons, so we'll kind of round out our learning on solutions today. So by the end of today's lesson, you should be able to calculate molarity of a solution when given a volume of water and an amount of solute. Remember, solutes, whatever we're going to dissolve into a solvent to make a solution. And you will be able to determine the number of grams of solute needed to make a solution of a given concentration. This is often what we have to do to make a solution in lab. Now, there are 5 different ways that we can express the concentration of a solution. We already saw 100 grams or amount of solute per 100 grams of water. That was table G. Using our solubility curves. Today we're going to cover molarity in parts per million. And previously we had learned about percent composition by mass and also by volume. Those are 2 different ways that we're able to calculate concentration. Concentration simply means how much stuff we have in a certain amount of space. So in order to calculate concentration, we need to define how much space we have, how much stuff we have in that volume, and the more stuff is going to mean a higher concentration, and the less volume is also going to mean a higher concentration, based off of the relationship of those variables in their respective equations. So these are our concentration equations that we find on table T. The 2 that we're going to cover today, parts per million and molarity. We've used this equation before, albeit briefly. On this one we have used a lot. Mole calculations. Remember, moles are the amount of stuff, and liters represent the amount of space. So we're going to jump right into some practice here. What is the molarity of a solution if it contains 2.0 moles of NaCl and 250 milliliters of solution? Well, we know that molarity equals moles per liter. Now we're looking for the molarity. So molarity we don't know, which means we should be able to find the number of moles and we should have the amount of liters. Now we know it contains 2 moles of NaCl, so we can use that right there. And that's going to be dissolved into 250 milliliters of solution. So this is 2 moles NaCl. And sometimes that happens there. Don't know exactly why, but it does. NaCl. The liters here, notice in our equation that this is liters. It is not milliliters. So we have to convert this here. And we have 250 milliliters. We know that in 1 liter there are 1,000 milliliters. So this gives us 0.250 liters. We just move that decimal 3 spots to the left. So now that we have our 2 variables here, we can plug these in. So we have 2 moles over 0.250 liters of solution. And this gives us a value of 8, or a molarity, that line goes again, a molarity of 8 molar. We pronounce that 8 molar. It's an 8 molar solution of sodium chloride. That's a shorthand abbreviation for solution there. Just want to make sure that we have correct units, moles, and that we have liters. And the common trick with this is that the volume is oftentimes given to you in milliliters, or, as in the next problem here, you're not necessarily given the moles. So this other type here, what's the molarity of a solution? So we don't know that. What is the molarity of a solution that contains 20 grams of NaOH in 2 liters of solution? Well, we know that our equation here is moles per liter. We don't know the molarity, which means we should be able to figure out the number of moles. We should be able to figure out the number of liters. Let's start with the moles. We're not given the number of moles, but we are given the amount of solute that we have in our solution. That's 20 grams. So we know we have 20 grams. We're going to have to convert that to moles using our mole calculation equation, which is the number of moles is equal to a given mass over the gram form of the mass. Now to find the number of moles here, we know the given mass is what's in the problem. That's 20 grams. And the gram formula mass of NaOH, I'm going to do this off on the side here. We have one of each of these. I'm going to round these to a whole number here. 16 grams per mole and 1 gram per mole. Add these up, and we get 40 grams per mole. And this gives us 0.5 moles. And those 0.5 moles are going to be dissolved in 2 liters of solution. So our liters match and our moles match the units that we need in our equation. I'm going to plug and chug here. We had half a mole in 2 liters of solution, which gives us a molarity of 0.25 molar. I'm going to make sure we put that capital M there to indicate that this is the molarity of the solution. So the trick with this one is having to convert your solute of 20 grams into moles so it'll fit in our equation here. At this point, you should be able to calculate the molarity when given a volume of water and an amount of solute. Now, as I had mentioned before, in lab, oftentimes we have to make a specific amount of a solution with a certain molarity. And we can rearrange our molarity concentration equation to solve for the number of moles, where we would simply multiply the molarity times how much solution we need in liters. So in order to do this, first, we want to determine the molarity of the solution that we want to make. We then determine how much solution that we want to make. So we could say, well, I want a 0.1 molar solution for our lab, and I want to make 1 liter of that. We multiply these two together, and it's going to give us the number of moles. So if I wanted to make a 0.1 molar solution of NaCl, if I multiply these two together, it's going to tell us how many moles of NaCl I need. If we're given milliliters instead of liters, we do have to convert to liters first. We want our units to always be in liters when we're doing any of our concentration stuff. We'll determine the formula mass of the solute, in this case NaCl. 23 plus 35. It's 58 grams per mole. Multiply the number of moles times the formula mass of the solute. So whatever moles we get here, we're going to multiply it by the mass of solute. And this will tell us how many grams of solute that we need. And that's what we're after here. This is now something that we can go and measure to make our solution, because we can't measure moles on a scale. So we have to do our conversions here. We can measure the grams that we need, and then we can dissolve that into the 1 liter of solution that we wanted to make. This is often carried out in a volumetric flask, which gives a real specific volume for making solutions. Okay, do a little practice here. How many grams of KCl are needed to make 500 mils of a 0.1 molar solution of KCl? So we're looking for how many grams of KCl that we need. So this we don't know. We want to make a 500 milliliter solution that has a concentration of 0.1 molar. So our volume is 500 milliliters, and this is going to be an issue because it's in milliliters. We know that in 1 liter there are 1,000 milliliters, so this gives us 0.500 liters. And we know the molarity is 0.100 molar. And that's what we're after as far as our solution. So the first thing that we have to do here, we know the overall molarity that we want. We know the volume that we want. We need to figure out how many grams we need. So what are we going to do here first? Well, we know that molarity is moles per liter, and to find moles, we multiply the concentration times the volume. Well, in this case, we have our units here, and these do not want to stay for whatever reason. I don't know why this does this sometimes. We have 0.100 molar times the volume that we converted. And this is going to give us the number of moles. We want, getting pretty slanted here, huh? 0.05 moles of KCl. Now, in order for this to work, see if I can pull this up here. We need to now convert this into grams of KCl. So we know that the number of moles is equal to a given mass over the gram formula mass. And if we rearrange this, our given mass equals the number of moles times the gram formula mass. We have the number of moles. It's 0.05 moles. And we're going to multiply that times the gram formula mass of KCl. And that's going to be, I'm going to do this up here. We have K at 39 grams per mole. And chlorine, I'm going to round it to the ones, 35 grams per mole. This gives us a total of 74 grams per mole. So plugging that in there, basically looking for essentially, what's that going to be, 5% of 74 grams. And that gives us a mass of 3.7 grams of KCl. So we're using two different equations here, our molarity equation and our mole calculation equation, to solve for how much KCl we'd actually have to measure. So we can go measure 3.7 grams of KCl on a scale, mix it with 500 milliliters of water, and that will make us a 0.1 molar solution. At this point, you should be able to determine the number of grams of a solute needed to make a solution of a given concentration. Parts per million, this is a Becker bottle, which has 1 million of those tiny little beads in it. And in this case, this is used to express concentration, but in the sense of how many pieces of that in a total of 1 million of those. Kind of a different way to put it. Where the amount of space in this example is, in the case of this bottle, there's 1 million pieces. And the amount of stuff is which specific color of bead we're after. And I know in this bottle here, there's one black bead in the entire bottle. So with parts per million, the stuff is the mass of solute. Or in this case, the number here, one black bead, and the space is the mass of the solution inside of 1 million total beads, or 1 part per million. So space will be represented by a mass of solution, and the stuff will be a mass of solute. So in this case, we're dealing with masses as opposed to moles. Why parts per million, you might ask? Well, it's used to determine trace amounts, or real small amounts of dissolved ions in drinking water. We can see this in a water quality report from the Water Authority. You can see all sorts of different types of dissolved ions and different minerals that are in your water, and they are represented most often using parts per million. They're also used to establish toxic threshold levels that are usually reported in parts per million, or sometimes parts per billion if it is a particularly nasty toxin that's going to give us a much finer scale, I guess. Because we're going to want a lot less parts. If something's really nasty, we're going to want to express that on a larger scale for parts per billion as opposed to a smaller scale. So we're going to want a lot less of that nasty toxin. And if we use parts per million, it might be a really significant number. So we kind of move our decimals around there a little bit to make the numbers a little bit more manageable. It's also used to measure the concentration of particulates in the air. Maybe for different type of smog components or carbon monoxide or things like that, we can determine how much of that particular substance is in the air. If there's a forest fire and there's a lot of ash in the air, we could use that as well. Air pollution is measured in parts per million, as is dust in a clean room at an electronics manufacturing plant, where dust can cause significant concern getting into electronic components, causing shorts, and in general just a dirty component is not going to be functioning as well as a clean one. Now we find this equation for parts per million on table T, and there's two things that we need. We need grams or mass of solute and grams or mass of solution. And then we're going to multiply that fraction by 1 million to give us our overall parts per million designation. So a quick little example here. What is the concentration in parts per million? So this is what we're looking for. We're looking for ppm, concentration in parts per million, of lead ions in 100 grams of tap water. So that's the total grams of solution, 100 grams of tap water. So grams of solution is 100 grams, and we want grams, with 0.0000450 grams of lead ions. So the grams of solute, whatever the smaller component is going to be your solute. The larger one is going to be your solvent or solution, depending how it's worded. Grams of solute here, this is pretty small. You could write that in scientific notation as well. 4.5 10 to the minus 5 grams. And those are the two things that we need. And then we'll multiply that fraction by 100. So our ppm is equal to the grams of solute, 4.5 times 10 to the minus fifth grams, over 100 grams of solution times 1 million. Now when we punch this into the calculator, what we get is 0.45 parts per million. And that's our concentration of lead in that sample of tap water. So for every million particles in that tap water, let's say for every 1 million molecules, we have 0.45 molecules of lead. Which out of a million, if you had 45 cents out of $1 million, is pretty insignificant. These numbers get much higher than 10, 20, 30, 40 parts per million. That tends to be a rather large number. Now, we might see this a couple different ways. A 50-gram sample of solution is evaporated to dryness. If the concentration of solute in the original solution was 25 parts per million, what is the mass of a solute that is left after the solvent has been evaporated away? So with this one, we have a 50-gram sample of solution. So we know that the grams of solution is 50 grams. And that's evaporated to dryness. So we're going to remove all the water from that solution, and we're going to be left with whatever was dissolved inside of it. Now the concentration in the original solution was 25 parts per million. So that was our ppm, 25 parts per million. And we want the mass of solute that is left after the solvent's been evaporated away. So the grams of solute, we don't know. So this is going to be a little different here. I'm going to plug this in as we see it in the equation. So 25 parts per million is equal to grams of solute that we don't know over 50 grams of solution times 1 million. Now, best thing to do here, we need to isolate the grams by itself. And what we're going to want to do here is move our million, and then we're going to want to move our 50 grams. So the first thing that we're going to want to do here, see, it's going to be, we're going to divide out by 1 million. To move that million to the other side. And what we're left with, this gets significantly smaller, to the minus 5 equals grams of solute over our mass of solution. And then we're going to multiply our 50, getting kind of smashed in here, and pretty slanted. Apologize for that. These cancel here. And the grams of solute that are left, 125 grams, or 1.25 times 10 to the minus 3 grams. And that's what we're left with, or solute that's left from that original 25 part per million solution that contained 50 grams of solution. So in this case, we're given the parts per million and have to solve for how much solute is left over. These are the two types that you'll most commonly see. Percent by mass is kind of a review, or by volume, using percent composition. We did this in lab. We did this in prior units. Using percent by mass of an element in a compound or percent by mass of water in a hydrate. And all we want to use is the equation on table T, mass of part over mass of whole times 100 to get our percent by mass or volume, depending on if we're given masses or volumes. We're going to do a quick example here using percent by mass. So you have a 25-gram sample of an aqueous NaCl solution that's evaporated and found to contain 2 grams of NaCl. What is the percent by mass of NaCl in this solution? So we're given a 25-gram sample total, and we know that it contains 2 grams of NaCl. Percent by mass of NaCl in this solution, well, the total, we're going to want part over whole. So the part is that 2 grams of NaCl. It's going to be the smaller amount. And the whole is our whole solution. NaClAQ. So the part we have here is 2 grams over 25 grams times 100. And this is going to give us 8%. The percent composition by mass of 2 grams of sodium chloride and 25 gram sample of sodium chloride solution is 8%. And if this was a percent by volume, this might say 25 milliliter sample and 2 milliliters of a solute or something like that. But we would treat them both the same way. If you guys have any questions, make sure you write them down and get them answered. Hope everyone has a great day.